Okay, so welcome back, and now we're going to start talking about how we set up related rates problems. So let's talk about the example that we were talking about before about the balloon. So we know that the volume of the balloon is related to the radius of the balloon. So let's think of this as a spherical balloon, okay? So if we look at the volume, and we say volume V, right? And so we would say the rate that the volume of the balloon is changing would be the derivative, so dV dt, okay? And then we take the radius of the balloon, and that's also going to be changing as well, okay? So that we would say is dr dt. And so we would say that both of these are related rates, right? This is a change in volume over change in time, change in radius over change in time. So as you're blowing up the balloon or filling up the balloon with water, both of these things are changing, and they're related to each other because, as we know, radius and volume of a sphere, if we're talking about a spherical balloon, are related to each other because the volume formula of a sphere is 4/3 pi r cubed, right? So the radius and volume are related in that regard as well. Okay, now, so what we're going to do is we're going to study examples of related quantities that are changing with respect to time, as I've shown here on the board. And we're going to look at how to calculate one rate of change given another rate of change. Okay, so what we're going to do is we're going to look at this using examples, and what we're going to do is look at the balloon example. So when we talk about inflating a balloon, let's use this one, okay? So let's say that we have this example, and we're saying that the spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second. It says, how fast is the radius increasing when the radius is 3 centimeters? So you've got this balloon, okay, and you're blowing it up, okay? Or you're using a compressor, right? And so we know that the rate, that the volume, right, they're giving you the volume. So the the balloon is being filled at a rate of 2 cubic centimeters per second. So that's volume, okay? Now given this rate, okay, and when the radius is 3 centimeters, at that instance, how fast is the radius changing? Okay? So, how do we handle that? How do we approach that? Well, here's what we're going to do. We're going to start off by writing down what is given. Okay? So the first thing we need to do is we know the volume formula, right? So here's the formula for the volume of a sphere. And this volume is given, and again, we want the units. So the volume is given as cubic centimeters, right? So this is cubic centimeters, okay? Now, since the balloon is being filled with air, both the volume and the radius are functions of time. That makes sense. So therefore, t seconds after the beginning, after you start filling the balloon up with air, the volume of the balloon is going to be what? Well, in this case, since this and this variable are functions of time, we would write this as a function. So 4/3 pi, right? This is just constant. And then, of course, this would be times r of t, right? And, of course, the units are cubic centimeters. Okay, so now we've got written in this form as a function, right? Both volume and radius are a function of time. Now what we're going to do is we're going to differentiate both sides with respect to time. Okay, and then we're going to apply the chain rule, see what we get. Okay, so we're going to take the derivative of both sides. So here we're going to get dv dt, right? Okay. Oh, hold on a second. I dropped a cube. Okay. And of course this is a constant, so we're going to take the derivative of this, so this is going to equal 4/3 pi. And then of course here it's going to be the chain rule, right? So it's going to be 3 times r of t squared, and then of course times the derivative of the inside, which is going to be r dr dt. Okay? Now here's the thing. We know from the problem that the change in volume is constant, right? Two cubic centimeters per second. Okay. So now let's simplify things. Okay. Now this right here is, again, understand that this right here is radius, which is a length per unit of time. So this is going to be in centimeters per second. Okay. So this is going to be 2 cubic centimeters per second equals, now 3 here, this 3 is going to cancel with this 3. So we're going to get 4 pi times r of t, quantity squared, times, dr dt, centimeters per second. And so now what we're going to do is we're going to solve for dr dt, right? That's what we're trying to find. So let's solve for dr dt. So dr dt equals, well, this is, we're going to divide by this. So it's going to be 2. I'm going to drop the, well, no, I'm going to keep the units so you can see what happens with units. So centimeters cubed per second divided by 4 pi r of t squared times dr dt centimeters per second. And of course, this is also, if we want to put the units here, this is also, oh no, that's a radius. So this is going to be centimeters squared, right? Because it's a radius at time t, so that's going to be centimeters, and then we're squaring it, so it's going to be centimeters squared. Okay, so now, what are we going to have? So now here's where we're going to enter the information. Remember, they told us when R is equal to 3 centimeters. Okay, so now what are we going to do there? So now let's simplify this a little more. So this 2 is going to cancel this 4, so that's going to leave 2 there. So we get 2 pi r of t squared. Oh no. This is in here. Sorry about that. Got a little anxious. Yeah, we're solving for this. I don't know. I ended up dividing by that. So this is it. And so now at 3, right, r of t, right? So now we're just going to simplify this. So this is equal to 1 over 2 times 9 times pi right? And so we've got centimeters squared on the bottom, centimeters cubed over seconds on the top, and that's going to give us centimeters per second, which makes sense because we're looking at a change in length over unit time. So that centimeters per unit time and seconds makes perfect sense. So based on our unit analysis, this makes sense. So we're on the right track. We're at least getting the right units. So now this is going to equal 1 over 18 pi centimeters per second. And so what does it tell us? It tells us that the rate of change in the radius, when the radius is 3 centimeters, is 1 divided by 18 pi centimeters per second. Okay? And that's it. So the point is what were the key things? We had to have a formula that related the two variables that we're interested in. We were given information about one rate, and we were given information about one of the other variables. And so this information here was important to know in order to solve the problem. We have to have a formula because that's what we're going to take the derivative of with respect to time. So the key is that we have two variables that are related to each other, and they're both changing with respect to another independent variable. Okay, so there are two dependent variables to another independent variable, time, right? So typically we're dealing with two variables that are both changing with respect to time, okay? But they're also related via another formula, okay? Just like in this example, we're interested in how the change in radius and the change in volume are related, right? So they have to be related with regard to another formula. In this case, we're talking about a spherical balloon. So the volume formula for a sphere is critical to that. So now we know that there's a relationship between radius and volume when you're talking about a sphere, right? Spherical balloon. And then we took the derivative of this equation to get another equation that related the rates. Okay, and so that's where this came in, right? So now we've got, this, right? And then so we simplify it. Okay, and so that tells us we've got now this differential equation that relates to variables that are changing. And then we plug in the information given in the problem, to solve for the other rate. Okay? All right, that's it. So now the next video I'm going to go through the steps, problem solving steps when it comes to related rates problems, and then we'll do more examples. Have a great day.